So I've suffered from RSI for a long time. I spent too many hours programming without a break, and now my hands are kind of messed up. But these days, I have a lot of tools that help me work regular hours without hurting myself. I have an ergonomic desk, chair, keyboard, one mouse for each hand, and sometimes I pull out the Talon voice dictation software, which is specialized for writing software by voice. But the most interesting tool is one I designed and built myself. It all started in 2022. I was going to a Halloween event, and my girlfriend was going to dress up as Sans Undertale. I was looking forward to it, even though I was boring and didn't have any costume myself. However, I never experienced this because instead I was sick in bed, running a high fever. Trying to keep sane, I was thinking about my setup. I use a fight stick with my feet as arrow keys, but this was not ideal, and the ergonomics of this was starting to hurt my feet. I considered, what if I had a big D-pad instead of a joystick? This would be much more ergonomic for my feet. In between waves of feeling like garbage, I sketched out how this design could work. Days later, I was recovering and started researching my idea. Surely this great idea already exists and I could just buy it. But it did not, so I built it myself. I had made some little 3D prints in Onshape before. This one was made to block out the light from the speakers in my bedroom. But this new project was far more complicated. I started out by prototyping a simple ball joint to make a D-pad. Does this even work? Yes, it does. Then I prototyped further and further and further. Wait, hang on. Is that a PCB? How did that get in there? I don't even know how to make one. At this point, I made a detour and learnt KiCad. I had never touched it before, but taking an existing open source keyboard design and tweaking it to my needs was pretty approachable after following some introductory tutorials. First off, my circuit board needs a USB port to plug into. The circuit also needs a processor that can talk to the computer through the USB port. Two of the pins on the port connect to two of the pins on the processor, forming what's called a differential pair. USB data, key presses for example, are sent between the device's processor and the computer over this differential pair. The processor also needs power. This is sent over another pin from the USB port. A return path is needed to complete this circuit. This is known as ground. Switches are needed to actually detect the key press. I used standard cherry-style switches that are used in mechanical keyboards. One pin from the processor is connected to one of the pins on each of the switches. The processor uses this pin to determine if the switch is held down or not. But the processor does this by detecting a voltage difference caused by completing the circuit. So we also need to route the switch's other pin to ground in order to complete the circuit. In this way, ground is kind of a dumping zone for when we need to complete a circuit. Here it is in KiCad. You can see the USB port, the processor, and the switches. You can also see there's a few extra components I neglected to mention, such as voltage regulation and flash buttons. I just left them as is from the keyboard design I copied from. And here it is manufactured. It felt magical unboxing my first PCB design. Now the only thing left is the firmware. I could have just used the QMK firmware, since this is pretty much just a keyboard. But I have some embedded software experience, and let's be honest, a bit of an agenda. So I wrote the firmware in Rust. I did this without a debugger, because I did not think to expose the debugger pins. Oops. One thing I really like about Rust is it brings the modern package manager into the world of embedded. The actual firmware implementation at this point is pretty small, about 150 lines of code. Most of the juicy bits are in the HAL, USB, and Keyboard libraries. I'm just gluing them together, but if I ever needed to, I could swap them out for a custom implementation. While I originally intended to rest my whole foot on the D-pad, I found it works much better to just rest my toes on it. To accommodate this, I designed a really long footrest. At this point, I have a working prototype that is actually nice to use. I have one problem though. The switches are soldered into the PCB, locking the top plastic panel in place forever. This sucks. I like to be able to disassemble things. Modern mechanical keyboards often use these fancy hot-swappable sockets to avoid this, and I want in on these magical sockets. So I do a new board revision. Along with the new sockets, I throw in some extra buttons, debug pins, and some extension port that I never even used. The entire device can now be disassembled and reassembled by hand. While it is a little rattly, the device is held together without any screws. Instead, it relies on friction and the spring of the switch is pushing up the D-pad, which makes it easy to disassemble and reassemble, but is also just really cool. Anyway, the main functionality is done at this point, and I've been using it for years and it is now a core part of my setup. I call it the D pedal, short for directional pedal, like a D-pad is short for directional pad. From using it, I found that keeping the left and right D-pad inputs unbound is helpful, since it's easy to bump them. Particularly dexterous users may find them useful though. I also have one D pedal for each foot. My left foot has a D pedal configured for mouse scroll, while my right foot has a D pedal configured for arrow keys. The software and hardware is entirely open source, so if you want to build your own, check the description. But I'm currently working on a redesign of D pedal that makes it more user-friendly, robust, and a slightly smaller form factor. I plan to make videos on this as I go, so subscribe if you want to see more.